Okay, in this presentation we are going to look at analysis of variance. An analysis of variance investigation with samples of size 8 for each of the four treatments results in the following ANOVA table. Just as a sort of quick remark there are four treatments and there are 8 in each. Okay, that's important actually. So overall there are 32, n equals 32. So the degrees of freedom there is n minus 1 for the total degrees of freedom. Okay, the number of groups minus 1, which I usually denote as p minus 1, is equal to 3. Okay, and then 3 plus 28 gives us 31. So we can figure out what the degrees of freedom for the residuals are. So the table is essentially given to us, but we don't have the test statistic there, nor do we have any conclusion for it. So the question is, calculate the observed F test statistic, and then state your conclusion accordingly. Okay, so that's a sort of, I'm going to go quickly through that one because really I want to do the part B and C are more interesting for me in this particular exercise. So I'm just giving a cursory glance to part A, but part B and C are a bit more important for this video. The treatment means are for group 1, 85, for group 2, 66.5, for group 3, 59, and group 4, the group mean is 95.5. Calculate the least significant difference between pairs of means using a 5% interval. Now, just as a quick remark, what is going to happen here is that they all have the same sample size. There's eight for each of the four groups. That's important. Okay, just make a note of that. It means that we only have to do this calculation once. And then just sort of listing in the means in order, illustrate the non-significant pairs using suitable underlining and comment briefly. We'll come to that shortly. So essentially the F test statistic is this value here divided by that value there. Okay, so it's 2,239 divided by 120. Okay, so the test statistic there is 18.66. That's fine. Now the degrees of freedom are 3 and 8, or sorry, 28. Okay, and using a 5% significance level, let's just work on that basis, or not. Or 1% significance here in this particular instance. If you want to use tables, the test statistic for alpha equals 0.01 is for degrees of F, the critical value here. This is the critical value. And from the tables 3, 28 and alpha level of 0.01, that will give us a critical value of 4.568. Now, you can actually sort of immediately tell that really whatever critical value or significance level you're going to use, that's still a very high test statistic. So the test statistic is greater than the critical value. We reject the null hypothesis that the population means are equal, so the p-value is going to be really, really low, basically. Okay, that's what we're just going to guess. So there's overwhelming evidence of a difference between the underlying treatment means. Okay, so they're a good bit different from each other. Now, as I sort of said before, I realize I ran through that very quickly, but really this is not the focus of this video. It's the stuff that's coming up next. So the least significant difference calculation. Okay, so for each pair of groups, okay, essentially you might go in ascending order. Okay, actually we will go in ascending order. We notice that the first group, the lowest mean is 3, okay, which is 59. And then the next lowest group is 2, and that's 66.5. Then the next lowest group is Y1, 85, and then Y4 going out a shot there, which is 95.5. So essentially what we have there is 3 comparisons that we might make. Okay, and we want to see if these sequential differences are big enough, are significantly different from each other. 59 to 66.5. That's a difference of 7.5. Is that significantly different? This is what? This is 10.5 from y1 to y4. Is that significantly different? And the last one there is 18.5. Well, the one in the middle. Okay. Now, essentially, how big of a difference is too big is the question to be, just to pass off. Okay. Now, we have three groups there, or three sort of different case-wise sequential differences. But essentially, because they all have the same sample size, we're just going to do the same calculation, the one calculation, and apply it 3 times. Essentially, what we're looking for is the least significant difference. Okay. The formula for the least significant difference is LSAD for AB, where AB is the first and second, the two groups. So that is our test statistic, our critical value, or quantile. It is the T degrees of freedom based on the within degrees of freedom, which we'll go back to shortly. In this case, it was 28. Times the, I don't know whether that equal sign is there. So it's the mean squared for within groups times 1 over NA plus 1 over NB. Okay. So T is a critical value from the T distribution. Okay, that's the degrees of freedom. Don't know why my pen is doing that. Okay. Actually, I'll just show you the figures here. Now, just actually in each of these calculations, it's 8 and 8. Okay. So we only have to actually do this once. We're going to take these values from the ANOVA table. Okay. Now, so the mean square for within groups is 120. 8 and 8 gives us 1 over 8 plus 1 over 8. The square root of that. This is the got from the table. It's this value here. It's a T test statistic based on the student T distribution, and we're going for 95% confidence. 95%. What's the question actually? 95%. 5%. Yeah, level there. Yeah. Now, just as a remark, these two numbers here for the least squares, the least significant difference, it's these two numbers here that we're particularly paying attention to. This gives us the degrees of freedom. Okay. And this gives us, this is the within and between. So within groups is the residual. And this gives us the within groups mean squared. Okay. So that's where these two numbers are coming from. So degrees of freedom is 28. And alpha over 2, okay. So from the statistical tables, that should give us 2.048. So now it's a little bit of calculator work, essentially. And we should get a least square difference, I say least square, least significant difference of 11.2, okay. Now, correctly, we should do one for each of the 3 successive case-wise differences, but because they all have the same sample size, we can use that same calculation each time. Okay, if they had different sample sizes, you just have to repeat and rerun the calculation accordingly. But we just sort of got lucky here. So let's just go down. That's actually that's the answer to part B. So, I'm just going to write it out here again. I'm just going to pause the video for a second. Now, I just quickly resumed it. So essentially, the case-wise difference here is the sequential difference there is 7.5. So there's not a significant difference between groups 1 and group 3 and group 2. Okay? Group 2 and group 1, there is a very significant difference. Essentially, just to go back over that, we're comparing the sequential difference there to 11.2. Okay? Is 7.5 greater than 11.2? The difference between the means, no, it's not. So they're not significantly different, 3 and 2. Groups 2 and 1, the sequential difference is 18.5. That is greater than 11.2. So there is a significant difference between groups 2 and group 1. And group 1 and group 4, 10.5. Close, but not close enough. So there's no significant difference between 1 and 4. So essentially, 3 and 2 are not significantly different from each other. 1 and 4 are not significantly different from each other, but the two groups are significantly different from each other. So that's the purpose of the least significant difference there. So essentially what we're doing in each case is comparing that to 11.2. Okay, that's grand. Okay, we'll leave it there.